Welcome to the third and final video in this series, using Excel to find an uncertainty using a graphical method. Just as a reminder, we've got to this point where we've recorded our data, we found a gradient, and we found our value for resistivity, but we haven't determined how precise this value is. Now to do this, we're going to create a second gradient to put on our graph. Now this graph is going to represent our gradient, a gradient that we could draw, a reasonable gradient that represents our points, but one that represents our uncertainty in where we position our gradient. The gradient is chosen by, in this case, chosen by the computer, but it's equally valid to include a gradient that passes through those error bars. One has to bear in mind as well that the line doesn't have to necessarily pass through the error bars. Remember what we said in the first video, that the error bar is a representation of if we took another measurement, where it would lie. If we took another measurement, say at 0.8 meters along the wire, then there's a 68% probability that it would lie within those error bars. But then there's also the probability that it would lie outside of those error bars. So we use them as a guide. The larger the error bar, the less certain we are of that value. So it has what you think of as less pulling power, pulling the line that you're drawing towards that point. So as I've been talking, what I've done is I've created a second column here of values. Now all I've put in for the moment is some standard values, number 3, some average value. And I'm plotting these in a graph, so I'm adding an extra data point. To do this, I right-clicked on the graph, went to select data and added an extra line. Now from this line, I'm just going to change it, so this as you double click on the points, you can change the line into a straight line to represent the points, and I'm going to get rid of those markers, which you can just follow through as I do. Once we have this line is going to represent our least certain line, our steepest gradient that we might possibly draw through these error bars. At the moment it's nowhere near that, but what I'm going to do is relate these data points now. Instead of these data points referring to just number 3, I'm going to change it now to be a straight line gradient, so in the form y equals mx plus c. Now I'm setting the values from these cells that I've just highlighted here for y equals mx plus c, and again I'm pressing F4 to fix it so that any one in this column, the x being our L value, now represents a gradient. And you can see, because I used the previous terms on this graph, it's a straight line which overlaps entirely the gradient that the computer drew. This gradient represents our best gradient. Now by using a trial and error method and tweaking these values in the gradient, remember this doesn't have to go through 0, this gradient, and pinning the gradient to 0 is a bad habit which a lot of people try and get into. There's always an uncertainty in your 0 value as well. Now we can tweak these values so we can choose a sensible gradient which goes through those extreme values which could lie within those error bars. Now this gradient that I've chosen is taking account for those values. The blue line now represents our best gradient, the one that we think best represents our data, and our red dotted line represents our gradient which we believe is an extreme version of what we might plot, so our steepest gradient. The difference between these two values now represents our uncertainty in the gradient. So all we have to do is take our steepest gradient minus our best gradient, and that gives us uncertainty in the gradient. Now as our resistivity is simply the product of the gradient and the area that we measure, the cross-sectional area, we can use similar rules that we referred to in the first video, combining the fractional uncertainties of the gradient and the cross-sectional area to determine the absolute uncertainty and the resistivity. From these values we get our final value for the resistivity. So our final value is 1.3 plus or minus 0.2 microohm meters. Now this value, we know it's accurate because it lies within the accepted value for the resistivity of nichrome, which is between 1 and 1.5 microohm meters. We have about a 16% uncertainty, and one of our largest source of error is in our experimental determination of the potential difference in the current, which we could improve to really improve this precision of our experiment and really lock down that value to give us a really accurate and precise value of the resistivity. So our final graph is shown here, where you can see the error bars, and hopefully you'll be pleased to see a reasonable fit for that dual gradient from which we've determined our value and an uncertainty. I hope you've enjoyed these videos, and I hope you find them useful and instructive in terms of trying to encourage students to use software. There is obviously the software which is bespoke for this, but those who are familiar with Excel to be able to use it to determine values and uncertainty, to really give a bit of a quantified description of their data and really be able to access the precision and accuracy of their final value. Thank you for listening. Finally, I'll just leave you with a couple of slides to read at your own leisure relating to determining uncertainty when your error bars are negligible, and whether you can use a statistical tool in Excel. Read those in your leisure and enjoy.